Welcome to Session 4. So far, our strategy has been muscular. Substitute, expand, solve. It always works. But today I want to show you something better. Some of the hardest-looking nonlinear systems on the SAT collapse in a single line if you notice their structure instead of attacking them head-on. The test writers know that most students will start expanding immediately, and they design problems that punish that instinct with pages of algebra. The student who pauses for 3 seconds and asks, "What shape is this?" finishes in one step. Today, we learn to see the shape. We have to start with the most expensive mistake in this entire course. If x squared equals 9, what is x? Most people say 3, and 3 is right, but it is only half right. -3 squared is also 9, so x equals 3 or x equals -3. Two answers, both real, both count. Now here's where the confusion comes from. The radical symbol, √9, does mean exactly 3. That's a function, and it returns just the positive value. But the equation x squared equals 9 is a different animal. It asks which numbers square to 9, and there are 2 of them. So the rule is, whenever you take a square root to undo a square, you write plus or minus. If x squared equals a, and a is positive, then x equals plus or minus √a. Let's see structure do its work. Consider x squared plus y squared equals 25, and x equals 3. Now you could panic. That first equation is a circle, and circles feel intimidating. But look what we were handed. X is already 3. Just put it in. 3 squared plus y squared equals 25. That's 9 plus y squared equals 25. So y squared equals 16, which means y equals plus or minus 4. 2 solutions, 3, 4, and 3, -4. And geometrically, that's exactly right. The vertical line x equals 3 slices through the circle at 2 heights, one above the axis and one below. The whole problem took one substitution, because we didn't fight it. And notice, if you'd forgotten the plus or minus, you'd have thrown away half the answer. Now, the pattern that shows up constantly, the difference of squares. X squared minus y squared factors as x minus y times x plus y. Memorize that shape. Here's why it matters. Suppose x squared minus y squared equals 8, and x minus y equals 2. The brute force approach: solve the second equation for x, substitute into the first, expand everything, and grind. That's a couple of minutes and several chances to slip. Instead, factor the first equation. X minus y times x plus y equals 8. But we know x minus y, it's 2. So 2 times x plus y equals 8. Divide by 2, and x plus y equals 4. Done. One line, and look what just happened. A nonlinear system became a linear one. If you want the actual values, you now have x minus y equals 2, and x plus y equals 4, so x is 3 and y is 1. Here's the second structure worth knowing by heart. X plus y all squared equals x squared plus 2xy plus y squared. Now rearrange that to isolate the part you usually want. X squared plus y squared equals x plus y all squared minus 2xy. Why is that useful? Because the SAT loves to give you the sum and the product, and then ask for the sum of the squares. Watch. If x plus y equals 4 and xy equals 3, what is x squared plus y squared? Square the sum. 4 squared is 16. Subtract 2 times the product. 2 times 3 is 6. 16 minus 6 is 10. Notice what we never did. We never found x, and we never found y. We didn't need them. The question asked for a combination, and the identity delivered the combination directly. And the twin identity, with a minus sign. X minus y all squared equals x squared minus 2xy plus y squared. So x minus y squared equals x squared plus y squared minus 2xy. Same ingredients, one sign flipped. Try it. If x squared plus y squared equals 10 and xy equals 3, what is the absolute value of x minus y? X minus y squared is 10 minus 2 times 3, which is 10 minus 6, which is 4. So x minus y is plus or minus 2, and the absolute value is 2. Now notice why the question said absolute value. Without it, there would be 2 answers, because we don't know which of x or y is bigger. The absolute value makes the answer unique. Read those bars carefully. Let's do one from your practice set. If x squared minus y squared equals 8 and x minus y equals 2, what is x plus y? Don't substitute. Look at the structure. The left side of the first equation is a difference of squares, so factor it. X minus y times x plus y equals 8. Now the second equation tells us x minus y is 2. Substitute that whole factor. 2 times x plus y equals 8. Divide both sides by 2 and x plus y equals 4. The answer is B. And look at the distractors. 2 is just x minus y handed back to you. 8 is the number from the problem. 3 is x times y. Every wrong answer is a real thing from the problem. One caution before we finish, because symmetry can also mislead you. When every equation depends only on squares, sign flips are free. If x squared equals 9 and y squared equals 4, then all four combinations work. 3 and 2, 3 and -2, -3 and 2, -3 and -2. 4 solutions, because nothing in the system can tell the signs apart. But the moment an equation contains a plain y or an xy, that symmetry breaks. Take x squared plus y squared equals 25, together with y equals x plus 1. That second equation is not symmetric at all. Flipping a sign changes it completely. So never add a negative twin automatically. Generate your candidates, then test every one of them in every original equation. Structure gives you speed, but verification keeps you correct. Let's recap the structures. 1. If x squared equals a, then x is plus or minus root a. Never lose the negative. 2. Difference of squares. X squared minus y squared is x minus y times x plus y. If you know one factor, you get the other by dividing. 3. X squared plus y squared equals the sum squared minus 2 times the product. X minus y squared equals x squared plus y squared minus 2xy. And the meta lesson: before you expand anything, look for a repeated expression or a known pattern. The SAT rewards recognition far more than it rewards grinding. Beautiful work on Session 4. You've now got the pattern recognition toolkit, and these identities will keep paying you back all the way to Session 12. Next time, in Session 5, we take on parameters, the questions that ask for, what value of k does this system have exactly one solution? It's the discriminant's moment to shine.